Okay, hi everyone. Welcome to the Space Science webinar series. Today's speaker is Dr. Abel Méndez. He's a professor at the University of Puerto Rico at Arecibo. He's the director of the Planetary Habitability Lab there. He's a planetary astrobiologist. His research focuses on the habitability of Earth, the solar system, and extrasolar planets. He's a NASA MIRS fellow. He has worked at Fermi Lab, NASA Goddard, Ames, and at the Arecibo telescope. His lab maintains the Habitable Exoplanets catalog, a database of potentially habitable worlds, which if you are in the field, you use it quite extensively. He's also does quite a lot of public outreach. He's very active on Twitter, so go ahead and follow him. So Abel, thank you so much for agreeing to give this talk today, and I am handing it over to you.
So thank you, Dimitra. My pleasure to be with you here. And thank you for the Center for Space Science and the New York University of Abu Dhabi for the invitation. So I will be talking about our work related to habitability, and then I will focus a little bit more about exoplanets at the end. So we have a complete context of how these habitability models could be applied for understanding the habitable universe around us. So where do we study habitability? So where, if you want to learn about this topic, what a reference, and of course you will think biology. So I go to biology to understand habitability. And the only issue is that you will be surprised that even the word habitability is not there in biology textbooks. So why so an important topic now trending because we are looking for life elsewhere? So why this particular word is not used in, and I was surprised of that. And that was my first approach to trying to learn this topic, which was trending in the early days of the NASA astrobiology program. And it was an important area. And I looked for this topic in biology and I didn't find it. But there were astrobiologists already trying to quantify this topic as something new. And there's this paper in 2007 by Everett Chuck and Melanie Holland, and trying to quantify this habitability problem in terms of something that we can measure and use for the astrobiology purposes. But I have the luck that during trying to get more understanding of this biology, so I am a physicist and astronomer by training, so I had to go deep into biology and looking for different papers regarding conditions necessary for life. I found this paper in 2008, I think. It's a 1993 paper. And in this paper, this is one of the rare papers that mentioned the habitability word in a biology paper, not related to astrobiology, and included a different term, habitat suitability. So this paper was for me the Rosetta Stone to understand why there were apparently no studies about habitability in biology, is because it was called a different way, it's a different term. So habitability in biology is called habitat suitability. That's the formal name. Now that I have this paper, I can look up the habitat suitability, and I was overwhelmed by all that much. And this appears in biology textbook this way to measure habitability, which were developed in the 1980s by biologists because of the need of the ecologists at that time, that every ecologist trying to understand habitability in the environment was using a different way to measure it. So this government organization from the US decided to have a workshop to organize all the input from the ecologists and establish a formal way to measure habitability, well, called habitat suitability. And now today we have thousands of these kind of papers, and that's and that was very revealing for us, because what we did in our laboratory, actually our laboratory was established to incorporate all these metrics in 2010, to incorporate all these metrics, habitability metrics from biology to the astrobiology purposes. So common assumptions about habitability, and I can tell you about this because I am using what we now know about how this is done in biology. So some common assumptions about habitability, especially in astrobiology. You can see that people sometimes say that we can define habitability. This is very complex. It's impossible to quantify because you require so many parameters, because these models try to determine if planets are habitable or not. So you won't be able to do this. So you see these statements repeat again. And this is not how things are done in biology. This is not how habitability is measured. In fact, so if we're having these methods in biology and we're studying places that are habitable, so why are we using them? Because we know they're habitable. These models are not created or developed to say is a place is habitable or not. That's a simple question. They try to answer a more complex question. Why? Why are they like that? And let me explain. So here we have a habitable place, two examples, Earth, deserts, dry forests, and rainforests. And what we presume not habitable, Mars, Moon, and Venus, at least at the surface level. And habitability models are not interested in deciding which one are habitable or not, but to tell the difference. Why we have here more biology, less biology, and why this is worse. And even if the place is not habitable or which one is worse? So I might have ordered this correctly. This is Mars, Moon is worse, and Venus is worse. But why is worse in particular? What makes a difference? So regardless if they're habitable or not. So this is a complex question anyway, but it's much easier to tackle than just say if the place is habitable or not. Because the problem is, if you really want to know if a place is habitable or not, this is not a question for a model. This is if you want to know that, then you have to find life there or put life there and see that it flourishes. Then you can say that place is habitable. So that's not the purpose of the model. It's not a life detection method. It just tells the difference, how suitable the environment for life is. And let me go to a very simple example to understand this process. And here are the requirements of life simplified. Follow the classical elements. And if you want to know if a place is habitable or not, now in biology terms, it has to have air, water, earth, fire, the classical elements. So that's easy to remember because you need a gas, liquid, solid phase plus energy. And why a gas, liquid, solid phase, this is the mass available for life, is because the elements required for life, hydrogen, carbon, nitrogen, oxygen, phosphorus, at least the minimum set for DNA construction, and life needs more than this, but at least this is the minimum for DNA, then not all these elements are in a single phase. Some are in the solid phase, some are in the gas phase, some are in the liquid phase. And you need these three phases to be connected, to flow, so all these elements get together to have life, at least, plus some energy source. So this is a very strong and simple way to look at habitability. And let me show you how powerful is this one. So on Earth, we have rainforests and we have these elements available in large quantities, these classical elements. So you have an atmosphere, you have a lot of water, in this case by rain, you have a solid because it's the surface, you have the ground, the nutrients, and then you have sunlight, the energy. So because you have these elements in abundance, you have a lot of life. And that life, that vegetation can support more complex life, like animals and then intelligent life. But it's amazing that in a planet so good for life, where life could adapt to anything, we have things like this. The driest deserts, just in a picture, they doesn't look like they can support any life at all. And that's amazing. If life is so strong that can adapt to anything, well, life tries to adapt to this. At least we know that microbial life could survive here. But if you want abundant life, and then life that you can see, complex life, multicellular life, then you need these ingredients in abundance. And the limiting factor here is liquid water. The same for when you have ice layers. You have a lot of water there, but the problem is that you don't have that water in liquid state, so you don't have ice forests. The clouds are droplets of water, but the problem is that you don't have those nutrients provided by the soil suspended for a long time in the atmosphere, so the system won't be stable enough to support an ecosystem. So it's a transient environment for life. The ocean surface, I should be expecting that ocean should be covered with plant life everywhere, but no, they look actually like a desert, again, a desert of life. And we know that life in the ocean tend to be more abundant close to the surface, to the beach, where there are those nutrients. So the problem is that these nutrients, because the farther you go from the coast, you have less nutrients. Luckily, we have dust that precipitates through the whole ocean. But otherwise, the problem is like in the clouds, is limiting of the nutrients. So if you go deep ocean, you again see a apparent lack of life. And the deeper you go, the problem is it gets worse because you have less air dissolved, less gases dissolved in the water, less energy from sunlight. And it looks like there's no. So all these places on Earth are habitable. They have microbial life at least. But if you're looking at a planet that has a lot of life, plant life, which support animal life, and then intelligent life, the only solution is this one. And that will require that your planet have land and rain are provided by an ocean. So you need a planet with land, an ocean, an atmosphere, and then an energy source to support such a large biosphere. Otherwise, you will end up for your planet to be anywhere like the other conditions that might be supporting anyway microbial life, but not abundant life or even complex life. So more formally, how is habitability defined in biology? As I said, habitat suitability. So habitability is defined as the suitability of an environment for life. This is the general definition. It's proportional to the carrying capacity of an environment. And carrying capacity is the maximum stable biomass that can be sustained by an environment. And are used to determine how a set of environmental factors impact life. So the basic fundamental equations is that habitability is equal to some study conditions divided by some standard of comparison. So you are so this is telling you the habitability is always measured relative to something. And you have to make sure that when you put your model here, it is proportional to the carrying capacity. That's not necessarily something easy to do, but so it's proportional to the biomass available for life. And this is the basic fundamental description of habitability, and it gets a lot complicated. So we are developing models based on this and adding a little bit more details. So here is the basic model that we are working on, which is which use these ecology models defined, plus also we incorporate the energy issue in life. So we can define habitability with respect to some variables of interest. So as I said before, we don't want to determine if the environment is habitable or not in the common sense, but we want to determine how the variables, environmental variables of interest, impact your habitability. For example, if you are considering temperature, you want to know how sensitive is temperature to the habitability of your system. You don't have to take all the variables, you just want to learn that variable in particular. Then you might add other variables, 3, 4, 6 variables, but you always start with as simple as possible and get your model more complicated, adding more variables. So this habitability is proportional to some fluxes, and now here is how I incorporate the classical elements. So you have to worry about the atmosphere's mass fluxes, so hydrosphere mass fluxes, your liquid phase, the solid phase, lithosphere mass fluxes, and energy fluxes. And here, these fluxes, this is still physics and chemistry, mostly, only that you are testing how your variables of interest might affect this. But the biology part goes in what we show here is the ecophysiology response curves. So how this life, and now you have to decide a particular life, how this particular life will respond to some of the variables of interest here. And you put all this together in a model, and then you can have a habitability equation for your particular case of interest. So here is an example, the same environments that I showed before qualitatively. Now we can quantify how good or bad are these environments. So here rainforest, because I told you already that this habitability is a relative to, so let's normalize to rainforests. So the rainforests are definitely the most habitable place on our planet. So normalize to rainforests. So ocean surface go well below that. Then deserts, then the deep ocean, then polar deserts, and clouds is the worst environment at all for life on our planet. So in other words, they provide the less mass and energy necessary for life. So let's work out a complete example of constructing one model, and this case for the surface of Mars. So here the step on how we construct a model. So you decide first, select the space at time of interest. Where do you want to learn the habitability? So I want to study the near surface of Mars. What variables? I am only interested in surface temperature and relative humidity because those are the variables that we measure there, or just are the important ones for life. Just have to select a comparison life. In this case, the closest thing that we can think about is endolitic life forms in the deserts. An environmental comparison, this is the Atacama Desert in Chile. And then with this variable of interest, we start with a general model of mass, energy, and put these variables in terms of the mass, how these variables contribute to the mass and energy and the quality factor for life. And in step 6, we always try that any habitable model that you try to work out the same model with an Earth example, just for validation. So let me show you some results here. So this is what we call it thermo-wet habitability, surface temperature and relative humidity. So these are the variables of interest. And this is the calculation of habitability in terms reference to the spatial region here. The region, this spatial region is what we know that terrestrial life requires. So temperatures about 255 Kelvin, 60% relative humidity. So this is the good region for life. So relative to this point here, we see here that the values on Mars surface is around the temperatures and relative humidities is they go around this for Mars to the bottom of the plot. So you see that you have 1,000, 10,000 less habitability by a factor of that less habitability than what you know is necessary minimum for life. So definitely that tells you, it doesn't tell you that Mars is habitable or not, the surface. It tells you how bad it is compared to your standard. So 1,000 or 10,000 less habitable than anything else. And we can plot this in terms of the evolution through a date. So here is just one date. This is the temperature to a typical day on Mars. This is relative humidity. In the morning, you have more relative humidity as expected. This is a wet soil, a more humid day. And habitability is at the bottom here in the plot. So you see the habitability start to grow through the day. And at some point by 3 a.m. to 4 p.m., with respect to Mars time, local time, then you have, it's more habitable. And it gets maximum. But the maximum, if you calculate the average here, the maximum compared to the Atacama Desert, and now here is compared to the Atacama Desert, is about 10,000 less habitable than the Atacama Desert. So the Atacama Desert is a stream for endolitic life, and you have here something that is 10,000 less habitable. So 10,000 less mass and energy available for life. And this is a fine way to say not habitable, but at least you have a number of how bad it is compared to some other environment. Moving forward, if we try to understand exoplanets, looking at our solar system, I love this plot because this plot shows you how much water we have on our planet, which is considered always a limiting factor for life because it's hard to have a planet with liquid surface water because of the temperatures required for that. But our planet is so blue, so nice. It's so blue that we should call it ocean instead of Earth. But no, it's fine to call it Earth because actually you put all the water on our planet in a droplet, it will be a small one with respect to the size of the planet. So Earth is right. And Mars have about the same proportional fraction, but in the long past. And it just lost that water. And if you look further away from the terrestrial planets, to the moons of Jupiter, Europa, and Ganymede, you see that they have a lot of water. They have a lot of water, more water than Earth, even that they are so much smaller. But that water is liquid only below a layer, probably of 10 kilometers. You will have that much liquid water. And Ganymede is more, but if you go farther away, then you have the moon Titan and Enceladus from around Saturn, and they have yet more liquid water below layers of rock and ice below their surface. So this tells you that water is a common element in the universe. It's just a chemical. It doesn't mean life. And but if you want life in abundance, like forests and animals, and then intelligent life, you need this planet with land and ocean. So if you try to work out the simple way, the classical elements below Europa, so you have ice and you have an ocean and you think about air, how much atmosphere is there? Not many gases dissolve in that ocean because you don't have atmosphere. You have water, okay, that's fine. But Earth, well, nutrients. So those nutrients are deep in the core of the planet. So unless there is a transport system, a convection system, they precipitate. So this ocean will be more diluted than our own oceans. And that's not good for life. And energy source, this is a dark ocean, no light. So you don't have that much energy. So you only rely in chemical energy from other sources, probably at the bottom. So you see if people trying to spit fishes or whales in this kind of ocean because there's a lot of water, is not. This is much worse than any place on Earth, than any ocean on Earth. And when we see those streams, we see actually that there is no animal life on those. This is a transient environment for animal life, but not a place to stay for long because there is not much to use from the environment. And we have life here on Earth that had the opportunity to adapt to those environments, but it's not, because we are working now not with evolution, but the physical chemical limits for life, which are a hard limit for life. So this is much worse. So in any case, because microbial life doesn't need much, then all these environments might be good for simple life, for microbial life. That's no big deal. But for animal life, complex life, that's a hard jump in the mass and energy requirements from the environment for this to hold. So how, going forward to exoplanets or planets around other stars, how to determine if the planet is potentially habitable? First, it has to have an habitable orbit. It has to orbit the right distance from the star for water to be liquid. It has to have the right size. It's too small, not atmosphere, too big, too much atmosphere, and water at the surface will be solid no matter the temperature if it has too much atmosphere. So Earth size should be close to nice. And Earth lightness, this is a comparison that we do for sorting planets. Once that you determine that the planet have the right orbit and the right size, then we can sort out this planet, which one are closer to terrestrial size and terrestrial orbit. And this is what we do with the Earth Similarity Index. But I have to stress out that this is a comparison, this is an open metric, and you can compare with any variables that you want, any properties. So this is not a habitability index, it's just a similarity index, which are used in ecology to compare different environments. One of the most important discoveries for exoplanets is the radius gap of exoplanets. So planets are like to be either small or big. And the issue apparently here is that around 1.8 or so, when you have the planet size almost 2 times Earth size, the problem is too big and it will trap a lot of atmosphere and it will be larger than expected. And it's smaller, then it won't take that much atmosphere and will be smaller. So this is something very interesting that is telling you that, okay, there is certain size. If we're looking for planets more like Earth, they are not supposed to have too much atmosphere, because as I say, if you have too much atmosphere, water will be solid at the surface, no matter the temperature. So planet below 1.8, 1.5, 1.6 Earth size should be are more likely to be rocky and to have not that big atmosphere. So this is our catalog of potentially habitable planets. We have in our catalog about 60 objects of interest, but these 24 are the best one. The best one because they are below 1.5 Earth radius. Still, we have some in our catalog 2 times Earth radius, but they could be anything. They could be rocky, but they could be also ocean water or a mini Neptune. So it's more uncertain if you go below 1.5 or 1.6 Earth radius. So these are the best candidates, 24 them, and here's Earth for comparison. And this is artistic representation. So the only true thing in this image is the size of the planet compared to Earth. And that we know that they orbit within the habitable zone. And depending on how much atmosphere they have, they could be good or not for life. So the problem is that the planets could be in this category. They could be tidally locked, always facing the same face to the star. One side will get too hot, and all water, if any, will go to the dark side and freeze over. So you won't have oceans, probably a small layer. You won't have rain, you won't have forests, and you know this planet will be only good for microbial life. Desert planets, again, not that much water for abundant life. Ocean planets, same problem. Don't expect in ocean planets to have whales, because if the bottom of the ocean is too deep, then there won't be too much nutrients at the surface level, where there will be in contact with the atmosphere and most of the light. So this will be worse than oceans on Earth, and this is only good for microbial life. So if you want planets with plants, animals, and intelligent life, so this is not our planet is not a coincidence. This is a requirement that they have oceans and land areas. So we can construct habitability models, the same models, but now applied to exoplanets. We don't know any details about the surface, but at least we can speculate about the possibilities and what will be the minimum requirement of factors that are necessary to understand these planets. Okay, so I am interested now in the global biosphere of the planet. So seeing the planet as a zero-dimensional model, the global biosphere, and what parameters will be necessary, the minimum necessary to measure their habitability. Well, at least to start in measuring the habitability. Planet size is important, and we know that for exoplanets, for most of them, not all. And surface temperature, we don't actually know the surface temperature for any of these planets. We can only estimate that temperature, but because that temperature depends on the atmosphere, and we don't know the atmosphere. We don't know how much water they have, how much atmosphere they have. And surface pressure is something that we have to estimate, considering different possible atmospheres. And ocean fraction, again, something that we don't know for exoplanets. And we are far from having this number for any planet. But at least this is, in theory, the minimum set to start assessing the biosphere of the planet from far away. So considering that this temperature requires some for this kind of life, I mean plant life, or in the ocean, phytoplankton, requires some temperature limits. We are evaluating and comparing our model with Earth, and we start with the same mass and energy model and depth parameter and convert to mass and energy. And we already validate this model with our planet, not because we have many planets with biosphere, but at least on Earth, you can divide our planet by biomes, by different regions of biology, where you know how much water they have, what are the surface temperature, they have pressure is the same everywhere, it doesn't matter here, radius of the planet is the same, but at least the surface temperature and the amount of water per region can be used to validate this model. And you have a linear relation between habitability and here for validation is a net primary productivity, which is a measure how much biomass is produced by unit of space and time. So we, at least this global, we can, in detail, we can use it to evaluate habitability. But the good thing here is that we can apply this model to other exoplanets. Again, we don't have what we want to, but at least we can explore the parameter space. And one of the systems that is very interesting for exoplanet studies is the TRAPPIST system. Is a system with 7 planets. Here we use from other part of our work how we need the surface temperature, but we are working in a model to estimate at least the range of possible temperature depending on the atmospheres you are assuming. So here we are assuming that they can have no atmosphere at all, until 10 bars atmosphere, 10 times the pressure of the atmosphere of Earth. So we are assuming this range. If this is the pressure range, then we can estimate the temperature range. And these red bars here are the possible temperatures. This is stellar flux, how much energy is Earth for comparison, 288 Kelvin, which means 15 degrees Celsius. And so that's Earth here, and this is in the y-axis temperature. And these are the TRAPPIST planets. Almost all of them here to scale are about the same size of Earth. And you can see that this planet, for example, D, could have much lower temperature, but also much higher temperatures than Earth. And there's even the faraway planet, even if it had a thick atmosphere, it can even go as close to the temperature of Earth. But for that, it requires a thick atmosphere. Mars, for comparison, is here. And red here is temperature estimates. Blue here is solar system object, Mars, Earth, and here's Mercury for comparison, and Venus. And for this planet, it has insolation larger than Venus, but it has 10 bars, not 90 bars like Venus has. Then it could be lower temperature. But it has an atmosphere like Venus, then it could be much larger temperature than even Venus. So, and the green here is our model. So we statistically apply this model with this temperature range, with what we know about their size, what we know, considering the pressure range, as I said, from 0 to 10 bars, and trying the different ocean fraction from no water at all to a planet covered by ocean. And statistically, you can then get some upper limit. So Earth, for comparison, is 1 here. So this planet D, upper limit is just 1/5 of Earth, and this is almost 1/3 of the habitability on Earth. So what this means? See, we have on Earth a global biosphere, which requires some mass and energy to sustain it. So these two planets, even in the best scenarios possible, they are by a factor of 1/3, for example, for planet E, has less mass and energy available for life. And you cannot go higher than that. So this is important to try this model, because at least we can explore possibilities. And so it's more limited to the potential to have a biosphere as large as our planet. So the habitable space in the universe, this is our solar neighborhood. We expect to have about 160, more or less, potentially habitable planets. When I say potentially habitable planets, it includes all the categories. So some might be tidally locked, some might be desert planet, ocean planets, little water, but available still for microbial life, or terrestrial planets. In the Milky Way, we expect in our galaxy around 50 billion, statistically speaking. In the whole universe, 5 trillion. But we can't forget about 5 trillion, 50 billion for the whole galaxy, because they are too far to learn more. So only the planets that are in our solar neighborhood, we will learn more about them in the next decade. And we might be the only terrestrial sites. So we are detecting here a lot of planets in the habitable zone, but maybe they are desert planets, tidally locked. So they are only good for microbial life, if any. And we might be the only terrestrial planet with land and ocean in our solar neighborhood. We don't know if this is the case, but this is something that we have to look for. So today we know the orbit and size of planet. So that's why we say they are potentially habitable. In the next 10 years on this decade, we will sample the atmosphere of this planet to learn more. So we have now this capability, and we have this capability. We have this capability now for big planets, but for smaller planets, it's difficult. So that's the goal. So if we find that the planet has water, carbon dioxide, oxygen, they will say, oh, well, this is like a habitable. But in 20 years or more, we will have details about the surface. And this is not that you see the planet like here, like a full disk with a land and ocean. You still see the planet. You're looking at the planet as a dot of light. And as the planet rotates, you will see it will become brighter and dimmer because of the continents, which are brighter, and the ocean, which are darker, telling you that this planet has continents. But if the planet is totally cloud covered, is the planet a whole ocean or a desert, or an ice body, you won't see any difference at all. In 30 years, now that you see the planet as a dot, maybe you will recognize the green in that light by a spectroscopy. You will recognize that there are, at the surface level, there is a layer of vegetation, at least grass or maybe forest. And then you will say, no, this planet is not only habitable, so only inhabited also, because you are detecting life directly. So 10 years, 20 years, 30 years, and you want to know more. But even the atmosphere, we are already doing this, because for this planet, LAH 3844b, we know that the planet, it has almost Earth size, but it has a flux 70 times. So this is a hot planet. But we know that this planet in 2019, we was a Spitzer telescope. We now have the capability, we're starting to have the capability to see the atmosphere of this planet, and we detected no atmosphere, or at least this planet have a very thin atmosphere. And this was announced in 2019. Another in 2019, K218. It has a radius of 2.3. This is probably a ocean world or a mini Neptune, but at least we're getting closer to the atmosphere of small planets, close to Earth size. The planet is in the habitable zone, so it receives about the same energy from the sun as us, from the star as us. And we detect water clouds, or at least water and clouds in the atmosphere of this planet. So this was by Hubble. So we are using current instrument and detecting the atmosphere of the planet. And most recently, March, for JG 1132, we detect the atmosphere of the planet. This planet is about the same Earth size. It's a hot planet, 19 times insolation, but at least we think it has methane and hydrogen cyanide and hydrogen in the atmosphere. So these were things that probably will be done in this decade, but we are already starting to do this with the current instrument. But in this decade, so Hubble and Spitzer were responsible for this detection. Kepler and TESS is currently in space. And this mission only detects the planets. And the next mission that will be capable of looking the atmosphere much better than the current instruments are the James Webb Space Telescope. So we will learn in this decade a lot about the atmosphere of this planets. And there are other missions plans, and there are also European missions. And but mostly all these missions are for planet detection, which is the planet size and the orbit. And in the far future, because there's concept missions, and we might have this more mission like James Webb, but more capable to see the atmosphere of this planet by other methods instead of transit. But what we need is something like this. This is Earth's close-up view. If we build a 10-kilometer, let's imagine that we build a 10-kilometer telescope. So Arecibo Observatory, which is 300 or was 300 meters. So a 10-kilometer optical telescope in this case. It doesn't have to be in one piece. In fact, it's better to construct it in different pieces, scattered through our planet or even in orbit. From the nearest star, we will receive the same picture of Earth like this. This is good enough to see vegetation, continents like that. But you don't see still that there are any intelligence there. Well, you don't see it in the close view here. But if we build a 100-kilometer telescope, at least in total area, even from the nearest star, we will see Earth like this. At least, and with this side, you will be able to see the individual island. Still, you will notice that you have here intelligent life, because our cities are small, and unless there is an advanced civilization covering with gray area everywhere here, then you will notice civilization, unless during the nighttime, you will see this planet and the sum of all the light from the cities, you will be able to notice the light from the cities. So yes, if you construct this huge telescope, which sounds like it's better to go to this planet. No, this is much cheaper to go to ever building a spaceship to go into any nearby planet. So we will, because this is much cheaper, we will do this first. And this is something that might take many decades to construct this huge, enormous telescope. But once they are built, we will see planets like a full disk, not like the current missions in 20 or 30 years. So, and then you will be able to detect intelligent life, if any, by seeing the light emission from cities. Is that ever possible? In conclusion, habitability models are essential to characterize habitable environments on Earth and beyond. This model help to integrate and quantify the effect of many parameters. So you have many parameters. It doesn't matter how many parameters you are, but you don't have to worry about all the parameters together. Just study a set of parameters at a time. Then to study the habitability. Habitability modeling is an emerging field. And this is very important because this is a goal of astrobiology. But now that we are integrating terrestrial knowledge and this mathematical modeling, there's a lot to do, a lot of things to do. And a big problem here, habitability is positively correlated with the abundance and diversity of life on Earth. This is true for Earth. More habitable place, or in other words, more places with more mass and energy available for life life is more abundant. True for Earth. Sounds logical. But we don't know if this is true elsewhere. And this is very interesting because we can use this to look for life as we don't know it. So if we see an environment with some requirements and we expect this amount of life, then we might see that it has more than expected. So definitely that will be a telltale that this is a process not like life as we know it. And that's why one of the reasons it's important to have these models attuned with terrestrial life, just to recognize when we see that something that it doesn't match our terrestrial knowledge, to recognize this is not nothing like Earth life. So thank you very much. So I am open to questions.
All right, thanks so much, Abel. That was a great talk.
Thank you.
And now we are open to questions. There is a question by Nosrat, and I'm going to read it now.
Yes, please.
I could not understand that how you can calculate an exact number for habitability. For example, for desert, why is it very small?
Okay. Let me jump, probably better to jump to that slide. Okay, this particular for desert here that I calculated this number, this is for the Atacama Desert. So depending on what desert, so this is as low as it can get for terrestrial desert. And this habitability is used only two factors: temperature and water content, which is available by rain or precipitation. So water is the mass available for life. It provides that's the provider of the mass, and the temperature is because it's related to insolation. That's the energy available for life. And all these environments are compared with the same variables: temperature and water available. And that's why you get this pattern. So depending on desert, you can go not lowest than this, because this is the Atacama. It's the worst case scenario. But you can get almost as close to 1 because it's dry forest, depending on the amount of precipitation that you will have. You can use other parameters too. You can use other parameters and, for example, calculate, because let's say, okay, let me think about relative humidity. Let me see how it impacts the environment or other factors. But we know that for terrestrial vegetation, the drivers are surface temperature and precipitation. So that's why I took this most important factor, but there are many other important factors.
All right. Vladimir, yeah, good to see you here. Go ahead.
Yes, hello. Thank you for interesting review on habitability, which is really a fundamental question with many parameters, as you said. And so I was just wondering, it looks like that I actually jump in a little bit later, what you mentioned, but one of the parameters that's it's a space weather. I mean, the stars that all exoplanetary systems that you mentioned that are close in exoplanets around M dwarfs, which are very, very active, magnetically active. They have strong magnetic fields, they have stellar winds, extreme UV emission, flares, possibly coronal mass ejections, and that will be, that will create detrimental conditions for the atmospheric pressure, the number one probably condition for habitability, right? So that's the first thing. The second, and when you talked about the conditions for the, gases that like including CO2, O2, it looks like that I haven't seen that N2 because the nitrogen is the crucial. I mean, the CO2 kills life, by the way. So, but N2 creates life. So if you have a lot of CO2, as you create acidic environments, so prebiotic chemistry cannot work. And the O2, actually, it is the recent acquirement of photosynthetic life on Earth, which wasn't present 4 billion years ago, and life was present without O2. Why do you think that O2 also is an important signature of habitability? Thank you.
Okay, perfect. Thank you, Vladimir. Okay, regarding your first comment about the N dwarf. So I'm showing here the plot. I hope you they see my pictures plot here?
Yes,
right
yes, I do. I do. Yeah.
Okay. So here we evaluated habitability, and as I told you, we surface we use surface temperature, the size of the planet, and we use pressure and ocean water ratio. The thing here is that when you use only these variables, which I call the minimum set, you see that it's not that good anyway compared to Earth. If you have other variables, as you mentioned, for N dwarfs, the space weather, the radiation, they are very active stars, very variable, especially at the beginning of the evolution. So, and that will make everything worse. So at least, with this, and this is why it's important to take this habitability, not try to, okay, let me put all the parameters and say, no, that would be crazy. You work by phases, and this phase tells you that it's already bad. So any variability of the star, UV, radiation, extra, yes, you can construct a model, which will only make worse everything. And there is the debate, strong debate on how good are M dwarfs for habitable planets. I think it shifts more to this. They are very bad for habitable planets, but they are the most common star anyway, and planets are easier to detect there. So that's why there's a lot of effort in M dwarfs anyway. They're easy to study. And regarding your second question about N2, definitely nitrogen. Nitrogen is so important. When you see the elements necessary for life, and nitrogen, it doesn't like to reform, is not rock forming element. Most of the nitrogen in the atmosphere. And then you need a large reservoir of nitrogen. But nitrogen, you know what, is hard to detect in exoplanet atmosphere. So even that we think in many of these models, we know what is best because we know life on Earth. There are some limitations on what we can measure, and nitrogen is very hard to detect in the atmospheres of this planet. Oxygen is hard, but detectable. And oxygen alone, we know now that is not a good biosignature because it could be produced abiotically without life in a planet. And probably oxygen and methane together is a better indicator because they tend to destroy each other. But these are the gases that are detectable. So we are very biased. And people complain, but what about planets with ice cover, with surface life? Yes, they are great. And we are exploring those in the solar system. But for exoplanets, for these planets and other stars, they are not detectable. So you will see a research approach bias to things that we can detect and discover now with our instrument. But all this, as you said, all this problem and thinking about the different gases, yes, they're important, but we can now speculate about how much these planets have. Thank you, Vladimir, for your question.
Yeah, thanks. Yeah, I want to quickly respond. Yeah, so the this plot, that normally people show with the temperature, the climate models, they based on the atmospheric pressure equals 1, right? The Earth's atmospheric pressure, and I think it's over the last 4 billion years of the Earth's evolution, the atmospheric pressure equals 1 bar. It's just momentary, I would say, that instant in terms of the Earth's life, instant pressure. So why do you think that this pressure 1 is just because number 1? That's because it appears after 4 billion years of the biological evolution. We need to take and apply to all exoplanets, but not why from 10 to the -4 to, let's say, 10. That because I would imagine it's orders of magnitude, and so 1 is probably some kind of a weird outlier, rather than a case that needs to be applied to those planets. I mean, there is no physical or chemical or biological reason to believe that 1 is a good number. And the second about N2, that, yeah, I agree with you that N2, of course, hard to detect. And in our Nature scientific report paper, we suggested that it's not N that should be detected, NO. Because that is, you have the harsh radiation conditions, that N2 is being fixated into N, and then CO2 into O. So you create a lot of NO and ON excess. And NO, for instance, is a great emitter at 5.3 microns. So in that paper, we calculated the and our planet actually emits at 5.3 microns, through NO every time we have a big flare on Earth. So the observations over the last 16 years with time spacecraft, as I discussed in that paper, show that this is a great emitter and one of the ways to detect N.
Yeah, Vladimir, that's great. And just a clarification, in this plot here, these red bars here are for atmosphere 0 to 10 bars of CO2. So it's not taking just 1 bar or something special. It's 0 to 10 bars. So in this climate model, I can go as high as 100 bars. So they will be big, huge here.
Yeah.
Okay, thank you. Thank you, Vladimir.
Thank you.
All right. Do we have any more questions? Srini, do you have a question?
No, this is very interesting. I know it is a very complicated problem, so I'll let it go.
We have another question by, where did Nosrat go? Yeah, Nosrat, go ahead.
Excuse me. Thank you for a very interesting talking. Maybe it is a very elementary question. Our life in the Earth is based on soil and the water. Is there any possibility for other material, other fluids, or other elements in the other planets to be used for making a new life? Only the life should be based on the water? This is my question.
Okay, just perfect. Just a perfect question. And that's why I like this plot of the classical elements, and not in terms of air, water, and earth and fire, but when I say gas, liquid, solid, and energy. Yeah, and I say here liquid on purpose, just to include other liquids. So there's the possibility, but if you consider that possibility, there's some restriction. All these elements, which at least are abundant, and we know are necessary for life as we know it, should be available in the phases. If you take all the liquid here, they should be available or be extractable. But the problem is that if you take on a liquid like ethane or methane, temperatures will be, for that to be liquid, temperature will be very low. So everything, growth and evolution, will move very slowly. The temperature range that are required for these environments are more restricted than water. Water has a 100 Celsius range of temperature, at least from to 1 bar of being liquid. But usually other liquids have a more restricted environment. So they're less likely for a planet to have those environments in liquid. And even so, if you consider, for example, coexisting different liquids, usually their elements are more abundant in certain way. So even if you are considering other life that is using other rare elements, if you have other abundant elements, life will be taken, the other life will take more advantage of that abundant elements. So that life will have to compete anyway with life that use, for example, liquid water, which is more abundant than other liquids. So it's not impossible, but anyway, I think about it, it just gets worse in terms of how capable that life will have. So I can think about only microbial life in any other liquid phase, not complex life, for example, plants or animals. Thank you, Nostra, for your question.
Thank you so much.
Yeah, Vladimir has another question. He's asking, why does this slide miss sulfur, the part of 4 amino acids?
Yes, that was on purpose, because I am putting here only the elements necessary for DNA. So there's a long list, and sulfur is very important for life, and iron, for example, and many other elements, about 20, almost 30 elements out of the periodic table. But I here just put the ones necessary minimum for DNA, at least for this molecule, regardless of that you also need other elements for life. Yes, but if you put sulfur there, then you know that for the ground, for the solid, phosphor and sulfur are the limited ingredients. They are usually in the solid phase, not in the gas phase. But also that depends on temperature.
Yeah, Vladimir, you have a follow-up question. Why don't you just ask him? Yeah.
Just thank you, Abel. Yeah, just saying that the because DNA is made of protein, is basic synthesized through proteins, and you need amino acids. Eventually, the DNA has sulfur in it, and sulfur not only the solid is also
yes, there are necessary for other proteins, but this is for
volcanic activity,
elements that made up DNA. Yes.
Yeah. So actually. So the volcanic activities, H2S and SO2, are extremely important. So the sulfur, it's another element, and also the I would mention the impact of metals, because without metals, if we go to the prebiotic chemistry and trying to talk about not about the just development of life, but the origin of life on exoplanets, you need to move to the prebiotic chemistry, and prebiotic chemistry will add also a lot of metals at the catalyst of the prebiotic chemistry reactions, including iron, magnesium, zinc. So that's the another point, that without, let's say, continents and without polymerization of the simple organic molecules on an exoplanetary surface, we will not have any building blocks of RNA and DNA. So just a comment. Thanks.
Yes, that's true, Vladimir. Thanks for pointing that out.
Thanks, Vladimir.
Thank you.
All right, if there are no more questions, then let us thank our speaker again. Thanks, Abel. Thanks a lot.
Thank you.
And
my pleasure.
I'll
Thank
see
you
you
for the
all
invitation.
next week. Bye-bye.
See you.
Bye.
Bye.
Bye-bye.